In this video, we'll talk about direct recombination in semiconductors. So to start with, let me take a semiconductor material which is in thermal equilibrium, and its energy band diagram is, let's say, like this, where this is EC and this is EV. Because of thermal equilibrium, there will be generation of electron hole pairs, and this generation we will call GTH, representing thermal generation of electron hole pairs. At the same time, when it is in thermal equilibrium, we have a recombination which we call RTH, and in equilibrium GTH would be equal to RTH, and the carrier concentration in this semiconductor would satisfy mass action law. Let me take this semiconductor to be a n-type semiconductor, where we can call the electron concentration in this as n suffix n, representing that electron concentration in n-type semiconductor under equilibrium to represent a 0. So we call this nn naught, representing electron concentration in n-type semiconductor under thermal equilibrium. And we call hole concentration as a p suffix n naught. So Pn naught. So Pn naught is the minority carrier concentration in this semiconductor. Nn naught times Pn naught would satisfy the mass action law because this is in thermal equilibrium. Now let me take this semiconductor and illuminate this with light so that we have generation rate which would which will not be GTH. Instead we'll have GTH plus GL. Because of the shining of light, we will have extra generation. Under this situation, let's say the electron concentration is Nn, which is actually not equal to the Nn naught, because there is extra carrier generation because of the light incidence. Now let's say the whole concentration is also Pn, which is not equal to the thermal equilibrium concentration, but the delta that changed compared to the thermal equilibrium condition, which is Nn is equal to Nn naught plus, let's say, del n, and similarly the Pn is equal to Pn naught plus del p. Now because of the generation of electron hole pairs as such, the del n should be equal to del p, because the number of electrons generated in conduction band should be equal to the number of holes created in valence band. And for charge neutrality reasons, this should be equal. Del n is equal to del p. Now because there is an increase in generation, for a brief moment that generation would be more compared to recombination. But when there is a equilibrium condition established, of course this is not thermal equilibrium because we are exciting the semiconductor with external excitation, which is light. So there will be recombination, but in equilibrium these two would be equal, which means the carrier concentration, let's say dp by dt or dn by dt, should be basically equal to 0, which means that this should be equal to the generation rate GTH plus GL minus the recombination rate should be 0. So let me just quickly summarize that we have a semiconductor in thermal equilibrium. We excited light onto the semiconductor, and we are taking semiconductor away from the thermal equilibrium so that the carrier concentration is higher, where Nn times Pn will not satisfy the Ni square. It will be greater than the Ni square because it is not in thermal equilibrium. If you keep the illumination like that, the semiconductor would reach a steady state where the carrier concentration in conduction band and carrier concentration in valence band would not change with time anymore. In that case, the rate of increase of carrier concentration with respect to time would be 0, which means the generation rate should be equal to recombination rate in equilibrium condition. Taking this into consideration, let me write that GTH plus GL minus R is equal to 0, and we don't know what is GL. So let me write this GL is equal to R minus GTH. And we can say this GL as net recombination rate, because we are seeing here the recombination rate which is higher than the thermal generation. This we can call it as net recombination rate. Now assuming the semiconductor is a direct bandgap semiconductor, we can say the recombination rate would be directly proportional to the electron concentration times the hole concentration, which tells us that if both the concentrations are higher, then the recombination would be higher. If both are small, then the recombination rate would be smaller. Now we can write based on this, taking a proportionality constant as beta times n times p. And similarly, we can write the recombination rate in thermal equilibrium as a beta times the thermal equilibrium concentration, which is Nn naught times Pn naught. We know that GTH is equal to RTH. So to find the net recombination rate, we know what is GTH, and now we know what is R as well. So let me write the net recombination rate here, which is equal to R is beta times N times P minus beta times Nn naught times Pn naught. Of course, this N is basically electron concentration in N type, so N suffix N, and this is P suffix N. We know N suffix N and P suffix N, which is given by beta times Nn naught plus del N, the excess carrier concentration, times Pn naught plus del P, excess hole concentration, minus beta times Nn naught times Pn naught. Now we can expand this further. Now we can cancel this beta Nn naught Pn naught and beta Nn naught Pn naught. Then we are left with these three terms. Now let me assume, because of the illumination of light on the semiconductor, the excess carriers generated are far less compared to the majority carrier concentration present in the semiconductor. Let me write the expression where del N or del P, which are both equal, is far less compared to the majority carrier concentration. In this case, let us find what is the recombination rate. Under this assumption we did here, where del N and del P are far less compared to Nn naught, we can reduce these three terms into one term. Well, let's say del N we are saying is already small, and we know that Pn naught is already very small because Pn naught is a minority carrier concentration. Now multiplication of these two terms would be even smaller, so that we can neglect this term under this assumption, and we can see how small this can be because del N and del P are too small. In that case, the multiplication of them would be even smaller, so we can neglect this term as well. So the net recombination rate can be written as U is equal to del P times beta times Nn naught. I'm taking beta times Nn naught in the denominator. It becomes 1 over beta times Nn naught. And we can write this as del P over the lifetime of minority carriers holes in this N-type semiconductor. So let me write this. U can be written as the net recombination rate as del P, which is nothing but Pn minus Pn naught over tau P. This is a very important expression which is telling us that the net recombination rate, as we take the semiconductor away from the thermal equilibrium, that there would be a process that triggers which will try to bring back the semiconductor to equilibrium, and that is the recombination rate. And if you see here, the recombination rate, the net recombination rate, is directly proportional to the excess carrier concentration. Let's say when the semiconductor is in thermal equilibrium, Pn would be equal to Pn naught. In that case, net recombination rate would be 0. Because the semiconductor is already in thermal equilibrium, it doesn't have to have this mechanism present. Now to understand this lifetime of minority carriers, let me take an example that we have a piece of semiconductor, whatever we assume. Let's say this is N-type semiconductor, and we are shining light across the semiconductor uniformly, so that the carrier concentration in this N-type semiconductor, minority carrier concentration Pn naught under equilibrium, would actually become, because we are shining light, it becomes Pn naught plus the lifetime of carriers tau P times GL, the generation because of the light excitation. GL basically tells us the number of electron hole pairs generated per unit volume per unit time. So we have time units here. So basically the units of this one would be number of electron hole pairs generated per unit volume, let's say centimeter cube. And we know this units is also number of holes per centimeter cube. It matches. So the concentration would change from Pn naught to Pn naught plus tau P times GL. The time variation of carrier concentration would look like this. Pn. We have here, this would be Pn naught, the thermal equilibrium concentration, and this would be tau P times GL. And let's say at T is equal to 0, we are turning off the illumination on the semiconductor. Then we only have the recombination rate that is acting on the semiconductor to bring it back to thermal equilibrium. Let me make some space here. So once we turn off the light at T equal to 0, the generation basically GL would be 0 because there is no light. But the carrier concentration would be changing with respect to time because the semiconductor would be trying to come back to thermal equilibrium. So we have this dP by dt, which is equal to GTH plus GL minus R, and this won't be equal to 0. But we know GL is 0 because we turned off the light. And we can write this as minus of R minus GTH. We know what is R minus GTH, which is net recombination rate. We can write it as minus of Pn minus Pn naught over tau P. So we can write this dP by dt as dPn minus Pn naught. This Pn can be written as Pn minus Pn naught. So the differentiation basically doesn't change. So it can be written as minus of Pn minus Pn naught over tau P. We can write the solution for this differential equation as Pn minus Pn naught is equal to some constant times e power minus t over tau P. And we can write this further as Pn is equal to Pn naught plus c times e power minus t over tau P. And we can find from this graph that we have seen what is the value of c. At t is equal to 0, we know that the Pn of 0 is equal to Pn naught plus tau P times GL. This is the excess carrier concentration created because of light. So we can rewrite this expression by finding the constant c. Pn as Pn naught plus tau P GL times e power minus t by tau P. So it means as time is increasing, basically the concentration here would exponentially decay, and as time tends to a high value, the concentration would reach thermal equilibrium concentration. The slope of this function at t is equal to 0 would meet a point here, which would be is equal to tau P. And we can say that tau P is the lifetime of holes, which means that a hole can be in excited state on an average for this much time. And similarly, in a p-type semiconductor, we can talk about the minority carrier concentration, recombination rate, and then we can define the lifetime of electrons there.